computer. Cool. Okay, so what I want you to start with on the pair deck, you don't need to solve this question. You might want to write the questions in the box down in your notes once you've answered the pair deck. But just think about, with the part I underlined, taking that part out of it, what could you do if we were attempting to solve this problem? Go ahead and put your answer in the pair deck. Okay, so again, not asking you to solve the whole question right now, just looking at, if we know we have 4 grams of NaCl, what's something we can do in order to solve that? The answer I was looking for is that we could find moles. Anytime you have grams, we can find moles. So regardless of what rest of the question is asking for, that's something you could do that would help you take a step forward in solving this problem. So I'll do that now, but you should be taking notes on it as well. Grams equals moles times molecular weight. We know we have 4 grams of NaCl. We can find the moles of NaCl as long as we use the molecular weight of NaCl. I saw someone said in the pair deck that we should use the coefficient. We never use coefficients for molecular weights. We don't even have a balanced reaction right now where we would have a coefficient. But even if we did, we don't use coefficients for molecular weights. So NaCl, Na is 23, Cl is 35.5. So that gets us a molecular weight of 58.5. When I do 4 divided by 58.5, I get my moles, and I'm going to say moles of what? My moles of NaCl, 3.068. So simply because I had grams of something, I found the moles. We'll see if that helps me solve this problem. Questions from anyone on anything so far? So still looking at the same question, now I've underlined a new part of it. I want you to think about things we've done so far that you could do. With the words NaCl, dissolving, what does that tell you? What's something you could do that might help? So go ahead and answer that in the pair deck. Alrighty, so a lot of people were able to get one of the 2 things, but not both. So that'll be good that this is a refresher for you. Just from the words NaCl dissolve. So even if the rest of this question disappeared, NaCl dissolve is one of our keywords for a type of reaction we know how to complete and balance. I will go ahead and post, it's a video I made last semester sometime of like a quick overview of those if you need it. I'll post that to Classroom later today as well. But whether it's dissolve or burn or formed, we have all these keywords that tell us, oh, we can complete and balance a reaction. So one of the 2 things I can do is complete and balance the dissociation, the dissolving reaction of NaCl. NaCl splits up into its ions, Na+1 and Cl-1. That's something I can do from the fact that it's NaCl dissolves. The other thing I can do, you learned last class, and that is, now that I have this reaction, I can find my heat of reaction by doing products minus reactants using that chart. So it's going to look a little messy here for a second while I go over to the chart, but going over to the chart, ions are on the 2nd page. So for Na, at Na+1, the sodium ion, we have a value of negative 239.7. For the chlorine ion, we have a value of negative 167.4. Let me write those down actually. So sodium is negative 239.7. Chlorine is negative 167.4. And going up to the 1st page of it, we'll be able to find NaCl. NaCl is here. It has a value of negative 411. So now I'm going to leave the chart so you can actually read the things I'm writing. And we can do products minus reactants. So the products, we have one, there are no coefficients. If there were coefficients in this balanced reaction, we would multiply each of these values by their coefficient, but we only have 1 sodium, so we only need 1 of the negative 239.7. We have 1 chlorine ion, so we need 1 of the negative 167.4. and then we subtract out our reactants. Also, there's only one NaCl, so only one value of the negative 411. And when I type this in my calculator, I get a positive, just double checking. Yes, I get a positive 3.9, and that would be kilojoules per mole. So just from the fact that there was a reaction mentioned via the word dissolved in this case, we can write out that reaction, we can solve the heat of reaction, and we've already done a lot for this problem. Questions on anything or things you want me to say again, differently, slower, you're not sure what to ask, but you're confused? Questions at all?
Wait, what's that called? Like is it called standard heat?
This?
Yeah.
We call it the heat of reaction.
Oh, okay.
Yeah, their standard heat of reaction is a thing, it just implies specific conditions. So we'll just look at heat of reaction. Good question. Other questions? Alrighty. I'm going to leave that up there for you. If you still need to copy it, go ahead and try this next one on the Pear Deck. Now that we have the moles of NaCl, the reaction written out, and the heat of reaction, what could we do to try to solve this question? Okay, some of you are still looking at your notes and thinking, and that's totally fine. I'm going to go ahead and show you my favorite phrasing I got on the Pear Deck for an answer. Now we can do the proportion thingy. I love that. It's true. What I was looking for is that we can do the proportion. The reason why we can do the proportion, first of all, the reason we need to do the proportion, because what a lot of you said is now we can do Q equals mCp delta T and find the change in temp of the water. We can't. The only heat we have is the heat of reaction. And that is specifically for, in this case, because there's a coefficient of 1 mole of NaCl. But we're not dissolving 1 mole of NaCl, we're dissolving 4 grams. So we don't yet know a Q value. We don't yet know how much heat the water gets to absorb or release as it changes temperature. We have to do the proportion in order to take all of this general information we have and turn it specifically into what this question is talking about, which is the situation when we have 4 grams of NaCl dissolving. So we have to do the proportion next in this particular case. What that looks like, I'm just going to erase some of what I have here and give me some more room. That proportion follows like the same pattern every single time, where typically we put the heat of reaction over the coefficient of something in the reaction. In this case, it's going to be NaCl because that's the one we have more information about. That will allow us to find some other amount of heat, the heat specifically for when we used, in this case, however many moles 4 grams of sodium chloride is. So we can do that proportion now because we have 3 of these 4 pieces. We know that the heat of reaction is 3.9 kilojoules. Because it was a positive 3.9 kilojoules, that tells us that the reaction is absorbing that heat. So 3.9 kilojoules absorbed. Sorry, that's a little messy. And that is per mole. Specifically, that's per 1 mole of NaCl because the coefficient of NaCl is 1 and the other information we have is about NaCl. We got someone asked in the chat, we got 3.9 from doing products minus reactants using that chart. Let me know if that helps. We're going to be able to find how many kilojoules of heat are absorbed by this reaction when we have, remember we did the 4 grams, we turned it into moles already, and we got 0.068 moles of NaCl. So we're able to do this proportion, and that's going to allow us, once we cross multiply, to know how much heat was absorbed by the reaction in this case. Person who was asking about the 3.9, can you tell me in the chat, because I can only see myself right now. Tell me in the chat if that helped.
Oh, what's the difference between the 3.9 and the X?
Great question. The 3.9 is the heat that's absorbed if we dissolved exactly 1 mole of NaCl. But in this particular problem, we're not dissolving exactly 1 mole, we're dissolving a different number of moles. So the X tells us how much heat we're actually going to absorb when we use 4 grams. Does that help? Does that help? I can only see me, so tell me out louder in the chat.
Oh, yeah, that helps.
Okay, cool. Thank you. Good. Other questions before we keep going? Okay, so then I can cross multiply this and solve. Let me just give myself a little more space here. So it turns out when I cross multiply this and solve for x, I get 0.267, and that is the kilojoules of heat that are absorbed by this reaction. And what's important for you to keep in mind moving forward is that that then is also equal to 0.267 kilojoules released by the surroundings. Sorry, it's so messy. That word says surroundings. So anytime we know that the reaction is absorbing, we know the surroundings are releasing, and vice versa. In this case, frankly, in most of the problems we solve, the surroundings are water. And so because in this case, the reaction has to absorb heat, it has to absorb it from somewhere, it's going to absorb it from this nearby water. That water is going to change temperature as it releases heat in order for the reaction to happen. Questions about that concept?
Will we ever deal with reactions that don't include water?
Even if so, water isn't in this reaction, right? Dissolving happens in water, but for our purposes for this class, the surroundings we're always going to use are going to be water because they're easy to measure. It's easy to measure the water's change in temperature. Does that answer your question?
Yeah, thank you.
Well, thank you for asking.
How do you know it's absorbed?
Great question. Way back when I first found this 3.9 number, it was a positive 3.9. It wasn't a negative. Like my calculator literally said it was positive 3.9. That's what tells me it's absorbed. If it were negative, it'd be released.
Thank you.
Thank you. Other questions before we keep going? Okay. Continuing on. Now that we know the heat absorbed or released by the reaction, in this case, we know the heat absorbed by the reaction was 0.267 kilojoules. Go ahead and tell me, what can we do? Where can we plug it in? What could a potential next step be? Okay, good. Not everyone finished, but that's okay. I just need to move us along a little bit. But yes, now we know how much heat the water in this case is releasing. We can plug that heat into Q equals MCP delta T. One thing you need to remember, and shout out to the person who wrote this in the pair deck, when we do Q equals MCP delta T, which is for the water, not for the reaction, but for the water, the Q is always in joules. So we're actually going to move the decimal to the right 3 times. So that's in joules, and we can plug in 267. That's how much heat the water is releasing. There are 40 milliliters of water releasing it. Water has a CP of 4.18. We can see how much that water would change temperature when it releases this much heat to the reaction. When I solve for that X, I'm finding the change in temp of the water, which is going to be 1.59. I'm keeping the numbers in my calculator. And make sure you're listening. I'll let you copy down the steps, but make sure conceptually this is making sense so far. Any questions? All of this is about the water. Okay, well, the water we know is releasing heat since the reaction is absorbing it. So when you release heat, your temperature goes down. The water started at a temp of 35. So since it's releasing heat, its temperature is going to go down by 1.59. And we know that the water must end at about 33.4 degrees Celsius. If the reaction were releasing heat, then the water would be absorbing it and its temperature would be going up. Questions on that? Okay, tell me in the chat if you need more time before I erase this.
Wait, what is the 267 from?
Great question. The 267 was 2.267 that I just moved the decimal over to turn it from kilojoules into joules. And where that 0.267 came from was after cross multiplying and solving my proportion, that was my X value. That was the amount of heat that the reaction absorbed, specifically for the 4 grams of NaCl.
Oh yeah, you had to move it to joules. Okay.
Yeah, exactly.
I got it. Thank you.
Thanks for asking. Wait, so why does it lose heat absorbing? So you have to clarify what the it is. The reaction is absorbing heat, which we know because that heat of reaction, the 3.9, was positive. If the reaction's absorbing heat, it has to absorb it from somewhere. The somewhere is water. So if the reaction's absorbing it, the water must be releasing it. And if the water releases heat, temperature goes down. Remember, if you give something heat, its temperature is going to go up. So if you get rid of heat, its temperature is going to go down. Cool. Thank you for asking. Okay, so we solved that problem. We were done, but there are a lot of steps there, and those steps don't always come in the same order. This isn't the type of thing you can just memorize, do A, do B, do C, do D. So I want to list out all of the things we just did as a summary, even though they don't always go in the same order. For solving these types of problems, sometimes you're just going to say, well, what can I do? Let me try this. Oh, I don't have enough information. Okay, I'll come back to that. One of the things we did, frankly, you can pretty much always start here, even if the reaction takes a different path, even if the problem takes a different path afterwards, is there's going to be some reaction that we can complete and balance, and then use that chart to do products minus reactants. So whether it's burned or dissolved or formed, all those different keywords. Again, I'll post a summary video of that. That's old, but you'll have access to it. If any of those keywords are used, complete and balance that reaction, find the heat of reaction. You can always start there. At some point, you're also going to be able to do a proportion. It was not the second thing we did today. If we tried to do the proportion, like second today, we would have gotten stuck because yes, we put the heat of reaction here, the one we just found after completing and balancing, and it goes over some coefficient from that reaction. But the other half of this proportion comes from the problem itself. It's going to be some other amount of heat. Maybe we're solving for it. Maybe we find it in a different part of this problem over some other amount of moles. Some problems have you find the heat and plug it into the proportion. Other problems have you find the moles and plug it into the proportion. But one of those things will have to do something before we're able to continue on with this proportion. Questions? Am I making sense?
Where do you get like the coefficient from? Like, how do you know which one to use?
Great question. So in that last problem we did, because they gave us 4 grams of NaCl, we used the coefficient of NaCl. If instead they had given us the grams of, they wouldn't, but they had given us the grams of the Na+1, we would have used the coefficient of the Na+1. So it's kind of like whatever else is mentioned in the question.
Okay, got it. Thank you.
Thank you. Okay, so I should have actually put these in a different order on the slide, but those moles, we're probably going to either get or plug into grams equals moles times molecular weight. That heat is ultimately going to be the Q. We just have to do some kind of like kilojoule to joule conversion. I'm sorry, this is so messy. Let's make it a little better. Sorry. what order we go in totally depends on what we're given. If we're given grams, we can find moles and then plug it into the proportion. But maybe we're asked to find grams, so that's our very last step. Maybe we have enough information about the water to use Q equals MCP delta T, so we can find that Q and plug it in and use that to get to my proportion. We have these 4 components of these problems. You have to do the problem solving of figuring out, well, what do I have enough information to do? What makes sense? Knowing that this green box is always about the reaction and the yellow box is always about the water. Questions on that? Okay. The last thing I want to talk about, I know I've been doing a lot of talking, and then I'm going to let you try one ideally before you go. We have a decent amount of time left. So how can you tell that it's this type of problem where you have all these things to do? Anyone willing to take a guess, unmute and ask? Again, your face won't show up on the recording and you're allowed to be wrong. Any guesses? How do you know it's this type of problem rather than something that was on your quiz?
It says like dissolves or burns.
Yes, that's probably the best, easiest way to know that there's a keyword that tells you that there's a reaction happening. When we were doing the heat lost equals heat gained, when it was like a hot piece of metal being put into water, there's no reaction happening. There was an exchange of heat, but there was no reaction. So we couldn't do a proportion about the reaction. We couldn't have the reaction do something and the water do something else. There has to be a reaction here. Any other thoughts? Cool. When I made these slides, honestly, that's the only thing I was looking for. But someone else said last period that you would get stuck if you tried to do anything else. In the last one we just did together, like NaCl, we didn't have the CP, the specific heat of NaCl, and we weren't being asked to find it. So doing MCP delta T equals MCP delta T wouldn't make sense. We don't know the specific heat of NaCl. We can't just solve it that way. We also, like if you tried to just do Q equals MCP delta T for the water, you have an M and you have a CP, but you're missing 2 other variables. You'd get stuck. You'd have nothing to do. So any of those quicker types of problems that we've done in the past just aren't going to work here. You don't have enough information without doing the 4 components I had on the last slide. Questions?
If you go back to the last slide, would all of your drawings be gone?
They would be, however, if I press undo a gazillion times, they won't be. So let me pause the recording for everyone else's sake. Give this one a try. If you get a right answer, if you get an answer before the end of the period, put it in the pair deck and I will write back to you on the pair deck. At the end of the period, depending on time or after the period, I'll film a solution just in case. So all I'm asking for is your best right now. Okay, so for this problem, let me give myself actually a little more space. This problem is going to be a different order than the last one. So the fact that we know we're burning CH4, don't let the in O2 throw you. All of our combustion reactions are in O2. We always add O2. We can do the complete and balanced reaction and do the heat of reaction just from the fact that it says burning CH4. So let me start there. And then the rest of the problem might feel like it's in a different order than the last one. For combustion reactions, we add O2. We make CO2 and we make H2O. My carbons are balanced. A 2 there balances my hydrogens. And then a 2 there balances my oxygens. Going and getting values off of the chart. CH4 has a value on the chart as negative 74.9. O2 you won't find on the chart. It's a pure element. Pure elements have a value of 0, so they're not even listed. CO2 has a value of negative 393.5. And since this is a combustion reaction, we're going to make sure to use water as a gas. So it has a value of negative 241.8, but we multiply that by 2 because of the coefficient in front of water. So when I do, let me turn that sound off. Whatever, I can't. When I do products minus reactants to find my heat of reaction, it's going to be negative 393.5 plus 2 times negative 241.8. Those are my products minus my reactants of 74.9. So negative 393.5 plus 2 times negative 241.8 minus negative 74.9. I get negative 802.2, and that doesn't seem quite right. So let me double check there easily. That gets me a heat of reaction of negative 802.8, 802.2 kilojoules per mole. That means this reaction is releasing heat because of the negative, and therefore water is absorbing heat. If I wanted to say, try and go and do my proportion now, because I know that the reaction releases 802.2 kilojoules of heat per, well, the question's asking about CH4, so per 1 mole of CH4, I'd realize that I'm stuck at this point. I don't know anything else that could be plugged into here. So I need to try going somewhere else in this question. Questions up to there? Okay, so looking back at the question, other information I have is water changing temperature. And hey, that water's temperature is going up. It's absorbing heat. It makes sense. The water's absorbing heat if the reaction is releasing heat. But that's enough to let me find a Q. Heat that the water absorbs equals mass of the water times CP of the water times delta T of the water, 10 to 95. That's a change of 85. So 710,600 joules are absorbed by the water. Or therefore, if I turn this into kilojoules also at the same time, 710.6 kilojoules were released by the reaction. And now that I know, now it's in kilojoules and now it's about the reaction, it can go in my proportion. And I'll know that's how many kilojoules the reaction released when I used a certain amount of CH4. When I cross multiply this and solve for X, I'll know that in this particular case, I use 0.886 moles of CH4. My grams of CH4 are my moles of CH4 times my molecular weight of CH4, which is 16. Sorry, it's messy. And we get 14.17. I kept the numbers in my calculator the whole way through. Sorry I fit so much on that slide. Questions on anything whatsoever for those of you who are still here? Alrighty, if you need extra practice, it's linked in today's slides. You can also email me and I'll send you the link if that's easier.